Okay, students, up to now we have been discussing about the model of an atom, the subatomic particles, and how they are arranged in an atom to give rise to different atoms of different elements. Then we discussed how to write electronic configuration of atoms. And based on that, we classified and divided atoms into the modern periodic table. Then you know how to identify the position of different elements in the periodic table based on their electronic configuration. Now we are going into a new topic, isotopes. The atoms with different mass numbers in the same element are known as isotopes of that element. So, for example, we will look at chlorine. Chlorine has two isotopes. Here you can see the atomic number of chlorine is the same. So, that means for chlorine, atomic number Z is 17. Therefore, number of protons equals number of electrons, that is equal to 17. But the mass number you can see here is different. In one isotope, the mass number is 35, and in the other isotope, the mass number is 37. That is the difference. Both are atoms of the same element, but they have different mass numbers. Then they are known as isotopes. How these numbers vary is that if you look at the mass number is equal to what? Yes, the sum of protons plus neutrons. We have already seen that the number of protons are the same. In both, it is equal to 17. So, that means what's the difference? The two atoms have different number of neutrons. So, atoms of an element with different mass numbers, because they have different number of neutrons, are called the isotopes of an element. So, here if we calculate for 35 chlorine, 17 chlorine, if we calculate the number of neutrons, it will be mass number minus proton will be equal to neutron. So, here neutrons 35 minus 17, that is 18 neutrons here. For the next type of isotope, 3717 chlorine, we subtract from 37, we have to subtract 17. Why? The mass number here is 37. So, here we have the value 20. So, one isotope of chlorine has 18 neutrons and the second isotope of chlorine has 20 neutrons. So, here again the identity of the element has not changed. Atomic number has not changed. It's the same value 17. Proton and electrons are the same 17, but the mass number is different because the number of neutrons are different. That is what we call as isotopes. Then we have the percentage abundance related to isotopes. That is, if you take a sample of chlorine, if there are 100 parts of chlorine in it, you don't get both isotopes in equal amounts. They will vary. So, out of those 100 parts, the amount of each isotope present is known as the percentage abundance. For example, if we take 100 parts of chlorine, out of that there will be 75 parts of 35 17 chlorine and 25 parts 37 17 chlorine. Based on this, if we write the equation for percentage abundance, we denote it as percentage abundance of 35 17 chlorine will be equal to the amount of 35 17 chlorine, that is 75 part, divided by 100 into 100. So that is 75%. Or directly, since we use 100 parts, we can directly take the value as the percentage abundance. 75% is the percentage abundance of 35 17 chlorine, and the rest is 25. So 25% is the percentage abundance of 37 17 chlorine. Not only chlorine, there are many other elements that have isotopes, and all these isotopes do not have the same percentage abundance. It can vary, and also all the elements need not have only 2 isotopes. They can have 3 isotopes as well. We will now look at hydrogen element and its isotopes. Isotopes of hydrogen. As you know, hydrogen is the most simple element. Just 1 proton and 1 electron. Atomic number is 1. But it has 3 different isotopes because it has different number of neutrons. And these isotopes are given different names: protium, deuterium and tritium. If we look at the subatomic particles, in protium there is 1 electron and 1 proton. That means atomic number is 1. There are no neutrons, 0. So, mass number is protons plus neutrons. It's only 1 plus 0, 1. So, mass number is 1. Using these two, if we represent hydrogen, that is protium, in its standard representation, we have to write the mass number on top and atomic number below and the standard symbol. 1 1 hydrogen is protium. If you look at this diagram, you can identify that easily. This is the subatomic particle present in the nucleus, only 1 proton and 1 electron. We'll look at the second type. Here you can see there are 2 subatomic particles in the nucleus. The number of protons can't change because the atomic number doesn't change. So, protons is 1, electrons here you can see is 1, but since there are 2 subatomic particles in the nucleus, that means there is 1 neutron. From that, if we find the atomic number, it's the same 1, but mass number 1 proton, 1 neutron. So mass number is 2. And the standard representation 2, 1 hydrogen. The third type of isotope is called tritium. Here the name has a relationship to its mass number. Protium 1, deuterium 2, duet is 2, deuterium. Tri means 3. So the mass number is going to be 3. 1 electron, 1 proton, atomic number 1. But there are 3 subatomic particles in the nucleus. 1 proton and 2 neutrons. So the mass number is 3. And the standard representation 3, 1 hydrogen. Protium, deuterium, tritium. Atomic numbers are same, protons and electrons are same. Mass numbers are different because the number of neutrons are different. So here you can see hydrogen has 3 isotopes. You should remember the names, the number of subatomic particles and their standard representation. With this, we finish the discussion on isotopes. Now we will see some patterns that are seen in the periodic table. When we discuss periodic table, I told you all that when elements are arranged into the periodic table, you will see similarities and patterns. First, we will discuss the patterns. Patterns seen in the periodic table. In the periodic table, it can be seen that the physical and chemical properties of the elements change according to a systematic pattern across a period from left to right and from top to bottom of a group. So, if we draw the simple format of a periodic table, you need to have 8 groups and the 4 periods. So, here this is across the period from left to right. You can see certain changes and down the group from top to bottom. And we saw that elements of similar properties come into the same group. They recur at regular intervals. So, if you take the first group, they are metals. But this metallic property can vary down the group and across the period. Those are the physical properties. Properties like metallic nature, boiling point, melting point, those are physical properties. Then the way these elements react with one another is known as the chemical properties. So both these type of properties show a systematic pattern across the period and down the group. Out of those properties, we will be looking at 2 properties. The first, ionization energy and electronegativity of elements. We will first discuss what ionization energy is and then how it changes along the period and down a group. First, ionization energy. The first ionization energy of an element is the minimum energy that should be supplied to an atom in the gaseous state to remove an electron to form a unipositive gaseous ion. I will explain that using an example. We will take sodium as the example. We have the sodium atom and it has to be in the gaseous state. Now this G written within brackets denotes the physical state of the element. So here when we put G, that means gas. Likewise, we can write S for solids and L for liquid. Here, according to the definition, the element has to be in its gaseous state. So the sodium atom has to be in the gaseous state and it has to lose one electron. When we say losing one electron, I explained this when I talked about ions. You don't write sodium minus electron. That is wrong. We have to write that electron on the other side of the arrow. That is not correct according to convention. So here we write the arrow and write again the sodium plus electron. Because we have removed one electron, sodium has one less negative charge. 11 positive charges and only 10 negative charges. So therefore, the overall atom gets a positive charge and becomes an ion. So now you can understand the definition. Supplied to an atom in the gaseous state to remove an electron to form a unipositive. Uni means one. One positive charge. To do this, we need to supply a minimum energy. Why do we need to supply energy? Yes, the protons in the nucleus are positively charged. The electrons revolving around in shells is negatively charged. And you know that there is an attraction between the positive and negative charges. Because the electrons are revolving very fast, they don't go closer and they don't go away from the nucleus. And the electrons are revolving in its definite path called the shell. What are we doing here? We are removing the electron from that shell. So that means we are breaking the attraction between the positive and the negative charge. The attraction has to be broken. To break this attraction, we need to give energy. That is why we say the minimum energy that should be supplied to an atom in the gaseous state to remove an electron to form a unipositive gaseous ion. And this is a simple equation to show the first ionization energy of sodium. And here the first ionization energy is a comparatively small value if we consider only one atom. So therefore, in order to obtain a value that is significant, we calculate the energy for 6.022 into 10 to the power of 23 atoms, which is equal to 1 mole of atoms. We will discuss what this value is and what mole of atoms are in a later lesson. But for now, you all have to remember that the first ionization energy has to be calculated either for 6.022 into 10 to the power of 23 atoms or 1 mole of atoms, not 1 atom, because it is a comparatively small value. And once we do this calculation, we get the unit of first ionization energy. Energy, you all know, the unit is joules. Here we use the kilojoule unit because it's a comparatively large value. And since we are calculating it for 1 mole, the unit will be kilojoule mole minus 1. As I said, you will learn this MOL mole minus 1 in later lessons. Now we will see how this first ionization energy changes in a periodic table. Given here is the first ionization energy values of the elements with atomic numbers. So you can see this is the simple version of a periodic table with only the first 20 elements, and all the values are given in the unit kilojoules per mole, kJ mol minus 1. And you can see in the first period, hydrogen and helium. Hydrogen 1310, this is 2372. Since there are only 2 elements, you can see helium is higher than hydrogen for first ionization energy. But if we look at the second period, elements starting from lithium up to neon, you can see that there is an increase in the first ionization energy values, but according to a certain pattern. First one, 519, 897, there is a small drop here, 799, then it keeps on increasing, again drops at oxygen and increases. The same pattern is seen in the elements of the third period. 1 to 2 there is an increase, third one there is a drop, and then 4, 5 there is increase, sixth one again there is a drop, and then it increases further. So you can see for the third group there is a drop in the first ionization energy. Again, for the sixth group, there is a drop in the first ionization energy. But you can see that the first ionization energy value is very high for all the group 8 elements when compared to the rest of the elements in the same relevant period. Second period, neon is the highest value. Third period, argon is the highest value. Even in the first one, helium is higher than hydrogen. So that means group 8 elements have the highest first ionization energy. This is what we talk about as the change of first ionization energy along the period from left to right. It shows a certain pattern. At the same time, if we look at the first group elements, lithium, sodium, potassium, you can see that the first ionization energy, when you go down the group, it decreases. Here you saw a pattern. Down the group, you saw that it is decreasing. Remember students, you don't have to memorize the values of first ionization energies, but you have to understand and remember the pattern. no need to memorize the values. That will be given to you for your exams. But you have to remember how the pattern varies. Now we will see how and why this change happens. The first ionization energy varies in a regular manner going from left to right in a period. So, it varies in a regular manner going from left to right. We will see the reason for that. If we consider, now there are 8 atoms, so we will have to obviously go for the second or the third period of elements. I will take the second period as an example. You can remember the order of elements. First period, hydrogen, helium. Yes, then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Now we will fill up the electrons to these atoms. Lithium has 3 electrons, so it will have 2 in the first shell and 1 in the second shell. If we take beryllium, atomic number 4, so 2 electrons in the first shell and 2 electrons in the second shell. Boron 2, 3. So 3 valence electrons. Carbon 4 valence electrons because it belongs to group 4. Nitrogen, again it has 5 valence electrons. 5 electrons in the last shell. Oxygen has 6 electrons in its valence shell. Fluorine, because the atomic number is 9, it has 7 electrons in the valence shell. And neon belongs to group 8. It has 8 electrons in its valence shell. Eight electrons. So, if I summarize, you can see the number of valence electrons. Valence electrons, lithium has 1, beryllium has 2, boron has 3, carbon 4, nitrogen 5, 6, for oxygen 7, fluorine and neon 8. At the same time, you know that the atomic numbers are increasing. So, therefore, number of protons are also increasing. In lithium, there are 3 protons. Beryllium 4, 5, 6, 7, 8, 9 and 10. Now, electron is negatively charged, proton is positively charged. 3 protons, 3 positive charges are going to attract 1 negative charge in the valence shell. There is a certain amount of attraction. When we go to beryllium, 4 positive charges are going to attract 2 electrons. Boron, 5 positive charges attracting 3 electrons. So, you can see when we go from left to right in a period, the number of protons increases. So, therefore, the attraction between the proton and the electron increases along the period. When something is attracted strongly to another substance, that is here, the electrons are attracted strongly by the protons, then it will become difficult to remove it from the atom. Therefore, we will have to supply a higher amount of energy. So, as you can see, along the period, the attraction between protons and the electrons, or the nuclear attraction on the electrons, increases. Therefore, it's more difficult to remove an electron. And we have to supply more energy when we go from left to right along the period. But there are other factors that affect the first ionization energy. That is why we saw a slight change. The third group had a drop. The sixth group had a drop in first ionization energy. But overall, you can see that the first ionization energy varies in a regular manner. The main reason, the number of protons increases, therefore the attraction between protons and electrons increases. So we have to provide a higher amount of energy. In that sense, the group 8 elements, neon belongs to group 8, or what we call as group 0. This has the highest first ionization energy in a certain period, because the attraction between protons and electrons are very, very high. Now we will look at how the first ionization energy varies down a group from top to bottom. The first ionization energy decreases from top to bottom. Now we will see why this happens. I will take the first group of elements as the example. So we have hydrogen as the first element, then lithium, we have sodium and potassium. By now, you remember the atomic numbers, so you are able to arrange the electrons into their energy levels. Hydrogen has only 1, lithium has 3, so 2 in the inner shell and 1 in the valence shell. Sodium has 11, so 2 in the first shell, 8 in the second shell, and only 1 in the last shell, that is the third shell. Then potassium again, 2 in the first shell, 8 in the second shell, another 8 in the third shell, and the last electron goes to the last shell. So this is the electronic configuration. All these elements have only 1 electron in the last shell, so that's why they belong to group 1. But you can see the number of shells increasing when you go down the group from top to bottom. So from top to bottom, number of shells increases. So because of that, you can see easily and clearly from the diagram, the size of the atoms increases. So size of atoms increases. When the size increases, what do you think will happen? Yes, here it is easy for the proton, the positively charged proton, to attract this negatively charged electron. The attraction is high. But when you come here, the distance is higher. The nucleus, positive charge, has to attract the negative charge that is a little far away. And when we come to this element, sodium, the last valence electron is more far from the nucleus. And to potassium, there are 3 more shells inside, and the valence electron is there in the outermost shell. And it is always the electron in the outermost shell or the valence shell that is going to be removed during first ionization. So down the group, you can see the size of atoms increases. Therefore, the attraction between the nucleus and the valence electron will decrease. And the energy that is needed to break this attraction will also decrease. Therefore, when you go down the group, the first ionization or energy of elements will decrease. So, as I said, since size of atoms increases, attraction between the positive nucleus and the negative electron decreases. Therefore, the first ionization energy decreases. So students, so far we have discussed how the first ionization energy changes along a period from left to right and how it decreases down the group from top to bottom. It's the same concept for all the groups. If you take group 3, boron and aluminium, the same. Ionization energy, first ionization energy decreases down the group. Same way, you take group 7, fluorine, chlorine, the first ionization energy decreases. Group 8, helium, neon, argon, the first ionization energy will decrease down the group. Now we will put all these data into a graphical form. The graph of ionization energy variation against atomic number. This is a graph that you have to understand and remember. Here you can see the x-axis has atomic number. So we are arranging the elements according to their atomic number. And the y-axis is first ionization energy and the unit is kilojoules per mole. You have to remember that. And in this, you can see the nice pattern of the first ionization energy changing for these elements. The variation in first ionization energy of elements. You can see hydrogen, helium is very high. This is the second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Then we have the third period elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. And the last period, potassium and calcium only. Here you can see certain special patterns. Always the group 8 has the highest first ionization energy. So it is group 8 has highest first ionization energy, that is the highest values. So they are at the top of the graph. And you can see group 1, hydrogen, lithium, sodium and potassium having the lowest values. They are there in the lowest point of the graph. So group 1 the lowest point. These are things you need to remember and identify from the graph. And then you can see when the graph, the element or the atomic number changes from one period to another. Period 1 to period 2. Period 2 to period 3. And period 3 to period 4. You can see there is a huge drop. So when there is a change in period, there is a large drop in the value. And the last pattern, you can see this zigzag change. If you remember, group 3 and group 6 have a drop. All the others increase. Similarly, group 3 and group 6 show a drop in the first ionization energy. If you remember all these, you can easily identify the elements of the first ionization energy graph. Remember students, for your exam or for a question, they will not give you or they might not give you the full graph with the atomic number and the symbols. They mostly give you part of the first ionization energy graph, and with that they don't use the standard symbols. They will just identify the elements as maybe A, B, C, D or X, Y, Z. If you know all these points, the patterns related to the first ionization energy graph, then you can identify the elements that are given to you. And then you will be able to answer the questions. So when you study this graph, look at it carefully and understand these patterns. That is why we refer to it as pattern seen in the periodic table. So that is the first property that we discuss for patterns seen in the periodic table. Now we will look at the second property, that is the electronegativity of elements. Electronegativity. Electronegativity means the ability of an atom of an element to attract the electrons of a bond towards itself when it is bonded to an atom of another element. I will explain that using an example. If we take a molecule where an atom of hydrogen is bonded to an atom of chlorine, this is hydrogen chloride. If you look at this molecule, there is a hydrogen atom and a chlorine atom. The bond means it's a pair of electrons. When you compare the ability of hydrogen and chlorine to attract the electrons towards itself, chlorine can easily attract the electrons towards itself. Then we say chlorine has a higher electronegativity compared to hydrogen. Now, if we go back to the definition of electronegativity, electronegativity means the ability of an atom of an element to attract the electrons of a bond towards itself when it is bonded to an atom of another element. It has to be an atom of another element. So, if it was a case where there was a hydrogen diatomic molecule or chlorine diatomic molecule, there is no electronegativity involved there because both atoms are same. But here hydrogen and chlorine are atoms of different elements. So now you can understand the meaning of electronegativity. Chlorine has the ability to attract the electrons of a bond towards itself when it is bonded to a different atom, hydrogen. So that is electronegativity. Hydrogen has less tendency to attract electrons, so we say it has less electronegativity. Whereas chlorine has more tendency to attract electrons towards itself, so we say chlorine is electronegative or more electronegative compared to hydrogen. And there are different ways of expressing electronegativity. That is, there are different scales to express electronegativity. Out of that, we will be using the Pauling's scale to express electronegativity of elements. According to the Pauling scale, different values are assigned to elements based on their ability to attract electrons towards themselves when they are in a bond with an atom of a different element. Now we will discuss the electronegativity values of the first 20 elements in the periodic table. This is the periodic table which shows the Pauling's electronegativity values of the elements with atomic numbers 1 to 20. If you look at this periodic table and the elements with their electronegativity value, you can look at the first element. It has a value of 2.1. That is the electronegativity of hydrogen. Then if we go to helium, that is in group 8, there is no value. Again, you go to the second period. Starting from lithium up to fluorine, there are values. But there is no value for neon. Again, argon. There is no electronegativity value. So, in a periodic table, normally if we look at group 8, they are noble gases. Because they are noble gases, they are less reactive or not reactive at all. They don't form bonds. Therefore, they have no electronegativity value. So, electronegativity values are not assigned to group 8 or group 0 elements. So, here because they are noble gases. So, group 8, they are all noble gases. Therefore, no electronegativity value. So, there is no electronegativity value assigned to noble gases. Now, we will discuss how electronegativity changes across the period. Here you can see, we will consider the first period only 2 elements. So, there is no way of comparing. Helium doesn't have an electronegativity value. We will take the second period. You can look at the values 1, 1.5, 2, 2.5, 3, 3.5 and 4. So you can see across the period from left to right, the electronegativity increases. Same for the third period. 0.1, 1.2, 1.5, 1.8, 2.1, 2.5 and 3 for chlorine. So across the period from left to right, electronegativity increases. Electronegativity increases. Now we will see how it changes down the group from top to bottom. If we take group 1, it starts with 2.1 for hydrogen, 1.0 for lithium, 0.9 for sodium and 0.8 for potassium. So you can see the values are decreasing gradually. Take group 2, beryllium 1.5, magnesium 1.2, calcium 1. Decreases down the group. Even the other groups, you can see when you compare second period and third period, the electronegativity decreases. Group 7, fluorine has value 4, chlorine has value 3. So students, down the group, as you have seen, the electronegativity decreases. So if I show that here, down the group, electronegativity decreases. That is the pattern you see in the electronegativity in a periodic table. Along the period from left to right, electronegativity increases. Down the group from top to bottom, the electronegativity decreases. So with that, if you look at all the values, what is the element that has the highest electronegativity out of all these? You can see along the period, electronegativity has to increase. Down the group, electronegativity will decrease. So therefore, if you look at all the values, fluorine is the element that has the highest electronegativity value. You have to remember that. Fluorine element with highest electronegativity value. Highest electronegativity. Out of all these 20 elements, fluorine has the highest electronegativity. The same way, if you look at all the values, down the group, electronegativity decreases and across the period it increases. So that means element with the lowest electronegativity has to be on this side. Here, if you look at the values, when we go down, the first two groups at the bottom have the lowest values, and out of those, it is potassium that has the least value for electronegativity. So in this periodic table, like fluorine having the highest value, potassium has the lowest electronegativity. Lowest electronegativity. You have to remember the two elements. The one with the highest electronegativity is fluorine, and the element with the lowest electronegativity is potassium. and noble gases do not have electronegativity values assigned to them. And also, if we look at all the values in order, you can see after fluorine, the element that has the second highest electronegativity value, you can see is oxygen with a value of 3.5. So, oxygen is the second highest in electronegativity value. Then the third element, there are two elements. You can see both nitrogen and chlorine have equal electronegativity values. So, the third elements are both nitrogen and chlorine. F is the highest, oxygen has the second value, then third value is for both nitrogen and chlorine. Remember students, you don't have to memorize all the values, but you have to understand these patterns. How it increases along the period from left to right, decreases down the group from top to bottom, and these elements with the highest and lowest electronegativity values. Now, we will look at a graph which shows all these electronegativity values. This is the graph with electronegativity values drawn according to their increasing atomic number. So, the x-axis gives the atomic number starting from 1 up to 20, and the y-axis gives the electronegativity values assigned according to the Pauling's scale. Now, in this you can see from hydrogen to lithium, both are in group 1. You can see there is a decrease. Then lithium to sodium, again there is a decrease, and sodium to potassium, there is a decrease. So, that means down the group electronegativity decreases. So, down the group it decreases. Then if you look at this part, starting from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, across the period. The same way, sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine increases gradually. So, along the period, electronegativity increases. So, down the group it decreases, along the period it increases. And also you can notice that always the group 7 elements, fluorine and chlorine, are at the top of the graph. So, the topmost point is group 7. So, here you can see I have marked group 7. Group 7 usually has the highest value. The same way you can notice that in all the groups, group 1, that is starting from hydrogen, of course has no other elements in the same period. Then we have lithium, sodium and potassium. Those are the group 1 elements. They have the lowest values in each period. So, when you are given a graph, they may not give you the full graph. It will be part of the electronegativity graph. You can look at the topmost points that will correspond to the group 7 elements, and the lowest values will be for the group 1 elements. In between, the electronegativity will increase in an order. And if there is a steep drop, that means it goes from one period to another period. So this is how electronegativity changes in a period. So these are the patterns that you see in a periodic table. We saw two properties. One was first ionization energy and the other one is electronegativity. You have to know how it changes across the period from left to right and down the group from top to bottom. And you should know to identify the changes given in the graph. Now we will go on to a new topic, metals, nonmetals and metalloids. Metals, nonmetals and metalloids. This is the complete periodic table with about 115 elements that exist in nature. And here you can see the different elements have been shaded with different colors. So in this, if you look at the major part of the periodic table, the elements are in blue color. That is because they are all metals. So majority of the elements in nature are metals. Then you can see hydrogen is in light brown color and these elements are again in light brown color. Those are the non-metals. In addition to these non-metals, you can see this group 8 that is colored in dark brown. They also come under non-metals. Although they are noble gases, they are non-metals. So we have the light brown and the dark brown colored elements. Those are the non-metals. And in this part, you can observe this stepwise pattern. And on either side of the stepwise pattern, you can see some green colored elements. These are called metalloids. The reason is they show properties between metals and non-metals. So therefore, they are known as metalloids. This is the complete periodic table, but for y'all, we will be considering the first 20 elements, the metals, non-metals and the metalloids present in that. So first we will discuss about metals. Metals. Of the elements identified so far, more than 80 are metals. So we saw in the periodic table, the major part of it was colored in blue. So that means there are more than 80 metals in nature. And in nature, these exist as native metals as well as compounds of metals. So when we say native metals, they exist as the metal itself. If the metal is not very reactive, then it can be found in the form of metal. In nature, if we look at examples for native metals, the metals that are present in their natural form, we can find some examples. That is gold, which has the symbol AU. Then we have platinum, that has the symbol PT, and silver. This also exists as native metal. Silver is Ag. So these are a few examples of native metals. And most of the metals are found in the form of compounds. For that, we can look at many examples. Metals like sodium, Then we have magnesium, even iron, Fe, and copper. These are a few examples of metals that exist in the form of compounds. Now we will discuss the physical and chemical properties of metals in more detail. First, the physical properties of metals. To identify a certain substance, an element as a metal, it should possess these following characteristics. So the first one, as you know, you have seen lot of metals. They are very shiny in nature. So the shine of metals, which you can always identify, is known as the luster of metals. So the first property is luster or the shine of metals. Then if you take a piece of metal and hit it on an object, or if you drop it down, you hear a ringing sound. That sound is known as sonorous sound. So sonorous property is another property of metals. Sonorous, that is the ringing sound when struck with another object. With another object. Okay. Then you know that metals can be hammered into sheets. That property is known as malleability. So metals are malleable. They are malleable. That means they can be hammered into sheets by applying pressure. The same way they can be drawn into wires. We use this in our household. We have sheets of metals for different purposes. We have the conducting wires. These are drawn into wires. That property is known as ductility. So ductile is another property of metals. They can be drawn into wires. We have seen luster, sonorous, malleable, ductile. And as I said, ductile copper wire is used to conduct electricity. And most of these metals are very good conductors of electricity. And also the cooking utensils, all the vessels, most of the vessels in the household are made up of metals because they can conduct heat very well. So metals are good conductors of electricity and heat. That is the next property. They are good conductors of heat and electricity. And also these metals are very dense. They have comparatively high density. They have high density. And also most of the metals exist as solids at room temperature. But there is an exception. What is there in a thermometer? The normal thermometer that you use at home has mercury in it. Mercury is a metal, but as you know, it is a liquid. So that is a liquid metal. It is an exception. So normally they are solids at room temperature. Room temperature. But except mercury. And the symbol for mercury is Hg, hydrogyron. So these are some of the common physical properties of metals. Now we will discuss the chemical properties of metals. Chemical properties of metals. Metals form positive ions or cations by losing an electron. You already know when we discussed first ionization energy. We used the example sodium. Sodium is a metal. It is a neutral atom that can lose an electron and form a positive ion. So here it becomes Na plus by losing an electron. This Na plus ion is known as a positive ion because of the positive charge, or it is called a cation. They combine with oxygen to form basic oxide. Here also we can use the example sodium. Sodium can react easily with oxygen, that is O2 gas that is present in the environment, in the atmosphere, and it forms Na2O, sodium oxide. We will learn how to write chemical formula towards the end of the lesson. So this is the chemical formula of the oxide formed between sodium and oxygen. And this oxide is a basic oxide, sodium oxide. Most of the other metallic oxides are also basic oxide, but the basicity can vary slightly. The oxides, when dissolved in water, form basic solution. So oxides, when dissolved in water, they form basic solutions. If we take the same oxide, sodium oxide, if it dissolves in water, it will form sodium hydroxide. This is a base, a basic solution. So because the oxides are basic, they dissolve in water and form the solution, which is also a base. Here sodium hydroxide is a very strong base. We will discuss the basicity in detail later. These are the common chemical properties of metals. Now we will discuss some examples of metals. First one is sodium. Here you can see in the picture, it is a shiny metal. It has a silvery shine. But because sodium is highly reactive, you don't get sodium as a native metal in nature. It always exists as a compound. So if I highlight some of the properties, this is very reactive, because it's highly reactive, it does not exist as a native metal, but it is present as compound. So it exists as compounds in nature. So as an example for sodium compound, if we look at the sea, seawater is salty in nature. That is because there are many salts dissolved in seawater, and one of the main salt is sodium chloride. That is an example of the naturally existing form of sodium. So as compounds, if we take an example, in seawater, we have sodium chloride. That is a salt. These are some general properties of sodium. Now we will discuss the position of sodium in the periodic table. Remember the atomic number? Yes. Sodium has atomic number 11. So if we write the electronic configuration of sodium, you know to do it, 2, 8, 1. So that means it has 2 electrons in the first shell, 8 in the second, and 1 electron in the valence shell. So what is the position of sodium? It belongs to group 1 because it has 1 valence electron, and it is present in period 3 because it has 3 shells containing electrons. So now we looked at some common properties of sodium, and we saw the position of sodium in the periodic table. Now we will discuss the physical properties of sodium. To identify the physical properties of sodium, we will do this activity first. So activity, identify the physical properties of sodium. To do that, I will need the sodium metal, and as I said, sodium metal is highly reactive. Therefore, you can't keep it as metal in the lab in an open space. So we have to take certain measures to store sodium in the laboratory. Usually, sodium is stored inside paraffin or kerosene. They prevent the reaction of sodium with atmospheric oxygen. And also, it has to be stored either in a brown colored bottle so that light doesn't make it to react, or it has to be stored inside a plastic bottle, but always in kerosene or paraffin. So since it is highly reactive, it's stored inside kerosene or paraffin. Paraffin is wax. Then we will need a forceps to take out the sodium from this kerosene or paraffin. And we need to place it on a porcelain tile. We have to make sure that it does not react with the surface where we keep it on. So a porcelain tile is ideal to keep the sodium and observe it. And since we are going to discuss and observe the properties, that is the physical property, we need to cut the sodium. To do that, I will be using a knife. These are the steps of the activity. First, you have to take the container containing sodium. It can be a brown colored glass bottle or it can be a plastic container. From that container, using the forceps, we have to take out a small piece of sodium, place it on a porcelain tile, and then we cut it with a knife. As we cut it into two pieces, you have to look at the surface. I will summarize the steps first as the method of the activity. So first, we have to take a piece of sodium from the bottle. So that will be either from inside kerosene or paraffin. Place it on a tile and observe. Place it on a tile and observe. Normally, metals should have a luster. So, we will have to observe and see whether sodium has a luster. Then, we have to cut the sodium piece using a knife. Okay. So, normally metals are very strong. We can't cut them with a knife very easily. But in this activity, we are going to cut sodium with a knife. You must be wondering why that is. We will first do the activity, then you will understand what happens, and also you will know how to do this activity, as well as you will understand the physical properties of sodium. Let us do the activity in the lab. Okay students, now we will do the activity to observe the physical properties of sodium, which is a metal. You all know that sodium is a highly reactive metal, so we have to store it inside kerosene or paraffin in the laboratory, and usually it is stored in a brown colored glass bottle. But at times we can also use a plastic bottle that is not transparent so that it doesn't allow light to go in to store sodium. I will open the bottle. You can see that there is paraffin inside. Now I will take out a small piece of sodium from the paraffin liquid and place it on the white colored tile. Here you can see this is the sodium that has a small amount of paraffin around it, and you cannot observe the shiny surface. Although it is a metal, it's not shiny because it's very reactive. It's a very dull, tarnished surface. But as you know, sodium is a soft metal, so I can cut it using a knife. Now, when I cut the sodium, I will hold it and cut it into small pieces. If you observe the cut surface, you can see it has a shine. And with time, as you observe it, the shine will decrease and finally it will completely go off. To that extent, sodium is very reactive with air. So, as you have observed students, sodium, because it's a metal, it does have the lustrous nature. It has the shiny surface which we call the luster. But because it is very reactive, the luster or the shine is lost very quickly. And also you saw that it is a soft metal because I was able to cut it with a knife. Okay students, now that you have observed the activity clearly, you have got an idea about the physical properties of sodium. What did we do first? We took the sodium out of kerosene. Then, was it shiny? No. The sodium metal was tarnished because it was reacted with oxygen, and also it had the paraffin or kerosene covering. So, there was no shine on the surface of sodium metal. So, that is the first observation. Sodium metal did not have the shine. Then what did we do? We cut it using a knife. So, we were able to cut with a knife. Can cut with a knife. So, this is a property that we call as soft metal. Sodium, because it can be cut with a knife or if it can be torn into pieces, then we call it a soft metal. So, here sodium, we were able to cut it with a knife, so it is a soft metal. And the cut surface, was it shiny? Yes. The cut surface was shiny. First had the shine. What happened with time? You saw the observation. The shine got lost with time. The sodium metal tarnishes because it reacts with air, that is the oxygen in air. Is it a slow process? No. It's a very fast process. So, sodium reacts quickly and the shine is lost. So, here we can say it tarnishes quickly. Or you can say shine of the cut surface is lost when exposed to air. So, those were the observations when we did the activity. So, from these observations, what can we conclude? The conclusion of the activity, that sodium is a reactive metal, so therefore it did not have the luster at first. So, here we can say it's highly reactive. And also we were able to cut it with a knife. So, therefore it is a soft metal. But the cut surface had the shine. So, that means it shows the metallic luster. So, it has metallic luster. But it again reacts quickly. So, that we have already concluded. Highly reactive. So, therefore, it tarnishes quickly. So, I'll write that again. It tarnishes quickly. So, these are the conclusions that we can obtain by looking at the sodium metal and cutting it with a knife. So, with this in mind, now we will discuss the physical properties of sodium. So, physical properties of sodium. Sodium is a metal, so it has the shine, the luster. So, it is a metal that has the metallic luster, and also sodium is a metal. Normally metals are high in density, but here you will see the density of sodium is less than water. So, density of sodium is less than water. It has a value of 0.97 gram per centimeter cube. That is the density of sodium. Density of water is 1 gram per centimeter cube. So, from that you can see sodium is less dense than water. And also sodium can conduct electricity. So, it is a good conductor of electricity. These are some physical properties of sodium. Now we will discuss the chemical properties of sodium. Chemical properties of sodium metal. Sodium shows a high reactivity towards oxygen. That you have already observed. When we cut the sodium into half, you can see the shine, but quickly with time it tarnishes. It reacts rapidly with oxygen in air to form the oxide of the metal. So, it quickly forms the oxide. I have already shown you all how to write the reaction for this. I will write it again. We have the sodium metal that reacts with oxygen in air and it forms the oxide, that is Na2O. As I said before, we will be learning how to write chemical formula. That is the last topic of this unit. But for now, you can remember these equations because that will be helpful for you in the next lessons as well. So, sodium reacts quickly with oxygen and forms the oxide of sodium. This is sodium oxide. Sodium oxide. And the chemical formula is Na2O. Sodium metal vigorously reacts with cold water. That is also a vigorous reaction. So, here we use the term rapidly, high reactivity, vigorously reacts with water. So, that means sodium is very reactive, forming sodium hydroxide and hydrogen gas. So, for that we can write the equation as sodium metal reacting with water H2O forming NaOH, that is sodium hydroxide, evolving H2 gas. It reacts violently with dilute acids and forms salt and hydrogen gas. For example, if we react it with hydrochloric acid, sodium will react with hydrochloric acid and it will form sodium chloride. This is what we call as a salt. A metal reacts with an acid and forms a salt. Here also there is hydrogen gas evolved. So, these are the products of sodium reacting with acid. But as we said, this is a very violent reaction. So normally we don't try this reaction in the lab. So here I will write it as a note. We do not try this reaction in the lab because it is very violent. But we can do the reaction of sodium with water. Now I will go to that activity. Activity, reaction of sodium with water. So for this activity again, I'll be needing a trough of water. Normally a trough is a large glass vessel where you can take a large amount of water and the area is also high. So you can use any vessel where it is a broad vessel so that you can have enough amount of water and there is lot of space for the violent or vigorous reaction as we discussed before. So we need a trough of water. We need the sodium metal because we are going to observe the reactivity of sodium. As we did before, to take out the sodium from the bottle, we need forceps. Sodium is stored inside kerosene or paraffin. We have to take it out using forceps. And to place it, we need the porcelain tile. And we'll be using only a small piece of the sodium metal. So to do that, we will need to cut and get a small piece. So for that, I'll be needing the knife. So the steps are very simple. We will take out a small piece of sodium from the reagent or the chemical bottle that is available in the lab using forceps. We'll place it on the tile and cut it into smaller pieces, and we can take the very small piece of sodium and put it into a trough containing water. Then you can observe the reaction very clearly. Already we discussed that during this reaction, sodium hydroxide solution is formed and hydrogen gas is evolved. We'll be able to see the gas evolving, but we can't see that sodium hydroxide is being produced. But we can confirm that it had been produced. Sodium hydroxide is a base, and there are chemical substances called indicators which give different colors with acids, bases and neutral substances. So here we will use another chemical substance, that is phenolphthalein. Phenolphthalein is an indicator that is colorless in acids and neutral substances, but it gives a pink color with basic solutions. So here, in addition to these, we will be using phenolphthalein indicator. Indicator to show that a basic solution has been produced. The same thing, to confirm that a basic solution had been produced, we can also use another material. That is the litmus paper. You have used litmus papers before in previous grades. They exist in two colors, the blue litmus and the red litmus. So we will test the solution using the two litmus papers. So here we have phenolphthalein and also blue and red litmus papers. So this is how we will be doing the activity. I have explained what we do first. Then to that solution, we can add a few drops of phenolphthalein and see whether there is a color change. At the same time, we can dip a strip of blue litmus and a strip of red litmus into the solution and check whether it is acidic or basic. So that will be the activity. Now I will summarize the method again for you all. So under method, we have to cut a small piece of sodium metal and then what do? We put it into a trough containing water. Put it into a trough of water and then you can see the observations clearly. After the reaction is over, we can put a few drops of phenolphthalein to the solution and also we can test it using the litmus paper. There is a different way of doing the activity as well. Before we put the sodium into the trough of water, we can add the phenolphthalein indicator. So that can be done before this or after this. Either way, if there is a color change, you can observe it clearly. So next, we add a few drops of phenolphthalein indicator. I will include that note. It can be added before putting the sodium in water. Both procedures will give you the same result. And finally, we test with red and blue litmus papers. This is the activity that we need to do to observe the chemical properties of sodium, mainly the reaction of sodium with water. Now let us go and do this activity in the lab. Okay students, now we will do an activity to observe the chemical nature of sodium metal. That is the reaction of sodium with water. As you know, sodium is a very reactive metal. So normally it reacts very fast with air and it tarnishes. I have a small piece of sodium on the tile which I took out from this bottle in which sodium was stored inside paraffin. And as you know, we can cut sodium using a knife because it is a soft metal. And when we put it into water, there are many observations that you can see. In order to make the observation more clear, I will be adding a few drops of phenolphthalein, that is the indicator, which will become pink in color. Phenolphthalein is a colorless solution, and when it is in contact with a base, it will become pink in color. So when sodium reacts with water, it will evolve hydrogen gas and the solution will become basic. So that when I add phenolphthalein to water that is inside the trough, you can see the observation clearly. You can see it's a colorless solution. I am adding just 2 drops of phenolphthalein. And also you might be wondering why we are using this huge trough. As I said, the sodium reacts very fast with water. So we will need a large space and a lot of water so that vigorous reaction doesn't lead to any kind of explosion. And also to be safe, I will be wearing the safety goggles. And now this is also a large piece that if we put that into water, it might lead to explosion. So to avoid that, I will cut it into smaller pieces. Observe the changes when sodium reacts with water. You can see the sodium metal going around, moving because of the evolving of hydrogen gas, and also you can see when it moves around the pink color of the solution forming. So when sodium reacts with water, it evolves hydrogen gas. So students, you saw the observations. What were they? Sodium floats in water because it is less denser than water and it reacts vigorously with water. That is why it moved around very fast. The movement was caused by the evolving of hydrogen gas. And as a result of this reaction, sodium hydroxide formed, and the sodium hydroxide gives pink color with phenolphthalein indicator. And again, we can confirm that there is sodium hydroxide, that is a base, using these 2 papers which I have here. You are familiar with these 2 papers. This is a red litmus paper and this is a blue litmus paper. Now with bases, the red litmus paper will turn to a different color. I will use both the papers. I will show you the color changes. Now you can see this is a red litmus paper. If I dip it in water, now you can see the red color litmus paper has turned to blue color. So that confirms the presence of base in this solution. I will also test it with a strip of blue litmus. Here you can observe that there is no color change. The red litmus turned to blue, but the blue litmus does not give a color change. So with all these observations, you would have understood how the sodium metal reacts with water, and the observations are now clear to you all. Okay students, now you saw the activity being carried out in the lab and you have a clear observation of what happened to sodium in water and the products that were formed. So now try to recollect all the observations that you saw during the activity. When we put a piece of sodium in water, it floats in water. That was your first observation. So sodium floats in water. This is a physical property. It confirms that sodium is less dense than water. Then what happened? It reacted vigorously and it moved around on the surface of water because of the hydrogen gas that was being evolved. And also you saw the hydrogen gas bubbles being evolved. With that, if you were listening carefully, you would have heard the hissing sound. So those are the other observations. Evolving of hydrogen gas. You can see it as gas bubbles. Then you can hear the hissing sound. And also you can see sodium moves around in water. On water. Then when we added phenolphthalein, the solution became pink. So the next observation, solution turns pink with phenolphthalein. And we tested it using the red and blue litmus papers. What happened to the red litmus? It became blue. What happened to the blue litmus? It does not change color. So red litmus turns blue. But blue litmus, no change. So we had many observations. You can remember all these observations from the activity. From these observations, we can come to certain conclusions. So the conclusions are sodium is less dense than water. This is a physical property. Then it reacts vigorously with water. Reacts vigorously with water. And you saw hydrogen gas being evolved. Gas bubbles evolve. So we know it is hydrogen, but we did not identify it as hydrogen. And also the product, that is sodium hydroxide, is a basic solution. And also we confirm that sodium hydroxide is basic by testing it with phenolphthalein and red and blue litmus papers. So sodium hydroxide solution formed is basic. So here also we know that it is sodium hydroxide. So we can confirm that it is a base using the test with both phenolphthalein and blue and red litmus papers. With this activity, you all know the chemical properties of sodium. That is a metal, and we have discussed the physical and chemical properties of sodium. Now we will discuss the uses of sodium. Production of sodium cyanide. When sodium metal forms cyanide by reacting with other chemicals, that is called sodium cyanide, and this is used in the extraction of gold and silver. When we discussed the properties of metals, we saw that gold and silver exist as native metals in nature. To extract them from the natural ore, we use sodium cyanide. Making sodium amalgam. Amalgam means sodium with mercury. Any metal with mercury is known as metal amalgam, which is used as a reducing agent in organic chemistry. You know about organic compounds. The study of organic compounds is organic chemistry, and all the reactions related to those compounds. In one of those reactions, we use sodium amalgam as the reducing agent. So make it to a different compound. That is a reducing process. You will discuss these types of reactions later. So we know that sodium is used as a reducing agent in organic chemistry. Then it is used in extraction of metals such as titanium and zirconium from their compounds. Again, these are different types of metals. They exist as compounds, and to extract the metal, we can use sodium. Production of indigo dye. Used to dye trouser materials, that is denim. You know the color of denim, a very dark bluish color which we call indigo. This indigo dye is produced from sodium, or sodium metal is used in the production of indigo dye. Used in the production of street lamps with yellow glow. Different metals have different colored glow. Sodium gives a yellow glow. So it is used in production of street lamps which give a yellow color light or yellow color glow. So students, now we have discussed some of the uses of sodium metal. Now we will discuss the properties and uses of another metal, magnesium. Magnesium, another example of metal. You know magnesium is Mg and the position of magnesium in the periodic table. You can remember students, it belongs to group 2. Why? Magnesium has a atomic number 12. So if we write the electronic configuration, it will be 282. So it belongs to group 2 and period 3. This is something that you already know. Now we will be looking at different properties of magnesium. As you can see, here is a strip of magnesium, a roll of strip of magnesium is shown to you. This is how we get magnesium in the lab. It is a very light metal. So it's a light metal and it is reactive. So because it is reactive, it does not exist as native metal. As you know, native metal is the metal existing as metal itself, not in the compound form. But here we don't get magnesium as a native metal. So, doesn't exist as native metal because it's highly reactive. But it is present as compounds in nature. Again, if we take seawater, magnesium chloride and magnesium salts are present in seawater. So, as compound, it is present in seawater. In seawater. One example is magnesium chloride. And also, since it's reactive, when you store this magnesium strip in the lab, it does have a shine, but that shine is lost and the metal tarnishes with time because magnesium reacts with oxygen in air. But the advantage here is the oxide layer that forms on magnesium acts as a protective layer. So, magnesium does not react further. Whenever we need to use magnesium for an activity or for some purpose, we can take a piece of the magnesium strip and we can clean it using a sandpaper. So, with the sandpaper, we can remove the oxide layer. Then you will get the shiny, lustrous magnesium strip. So, it does have the metallic luster is present. Is lost due to reaction with oxygen. So, there will be an oxide layer. Over the metal. This can be removed using a sandpaper. So, those are some common properties of magnesium. Now, we will discuss the physical properties of magnesium. Physical properties of magnesium. It is a good conductor of both heat and electricity. Normally, all the metals are good conductors of heat and electricity. So, magnesium is a metal that also can conduct heat and electricity well. And it has a higher density than that of water. And the density is 1740 kilograms per meter cube. Water has a density of 1000 kilogram per meter cube. That is equal to 1 gram per centimeter cube. You can give the density in any unit, kilogram per meter cube or gram per centimeter cube. So, here magnesium is more denser than water. These are the physical properties of magnesium. We will discuss the chemical properties of magnesium. Chemical properties of magnesium. When heated in air, magnesium burns with a bright white flame, giving white magnesium oxide. So, you can easily burn a strip of magnesium holding it to a flame, it will burn in air and it will produce white color magnesium oxide. It burns with a bright white flame. That is a prominent observation. And this will lead to the formation of magnesium oxide. If we write the reaction, magnesium plus oxygen will give you magnesium oxide. So as I said before, you have not learned the way of writing chemical equations, but this will be useful for you in the lessons hereafter. So for convenience, I am showing you all the chemical equations as well. Then magnesium does not react with cold water. So if you take a strip of magnesium and if you put it into a test tube containing normal water, cold water means water at room temperature, there will be no change. You can retrieve the magnesium strip back. So magnesium with cold water, there is no reaction. But it reacts with hot water. And during that reaction, magnesium hydroxide and hydrogen gas are formed. So magnesium reacts with water, but here you have to mention it's hot water. And this produces magnesium hydroxide and hydrogen gas. Magnesium with hot water, magnesium hydroxide and hydrogen gas. When the metal is strongly heated in steam, you know students, than boiling water, steam has more heat. So there the reaction will be more easy. So when the metal is strongly heated in steam, magnesium oxide and hydrogen gas are formed. So here again there is a difference. Magnesium, water, but in the form of steam. So that is gaseous state. So Mg plus H2O, but here we have to mention this is steam. Here I said it's hot water. So with steam, it will produce magnesium oxide and hydrogen gas. So here you can see both these reactions. This is hot water, this is steam. Here you get magnesium hydroxide and hydrogen. Here you get magnesium oxide and hydrogen. So magnesium reacts with water in 3 different ways. Cold water, no reaction. Hot water, magnesium hydroxide and hydrogen. Steam, magnesium oxide and hydrogen. You have to understand these 3 reactions clearly. Magnesium rapidly reacts with dilute acids and forms the corresponding magnesium salt and hydrogen gas. Here it reacts rapidly, not a vigorous or dangerous reaction. So we can try this reaction in the lab. So magnesium reacts rapidly with acids. We can react magnesium with dilute hydrochloric acid. Hydrochloric acid is HCl. So it will form the salt of magnesium, that is magnesium chloride. This is magnesium chloride. That is the salt produced in this reaction. Magnesium and hydrochloric acid gives magnesium chloride and hydrogen gas. So, as you can see, reacts rapidly with dilute acids. This has to be dilute HCl. So, that is something you have to remember and forms the corresponding magnesium salt and hydrogen gas. These are the chemical properties of magnesium. Now, let us do some activities to observe these chemical properties. The first activity, burning magnesium in air. The materials needed are magnesium, that is what we are going to use, magnesium, the metal, then we will need a pair of tongs. This is to hold the piece of magnesium strip to the Bunsen flame, and we will need the Bunsen burner. A very simple activity. We need to take a strip of magnesium. We have to check whether it is shiny and clean. If it has the oxide layer on top, mostly it does, then we will have to clean it using sandpaper. So, I will just include that step here. If covered with oxide layer, then we need to clean it with sandpaper. So, when we do the activity, either we use a clean magnesium strip that is shiny, or if it has the oxide layer, we clean it with a sandpaper. Then we use the pair of tongues and hold it to the Bunsen flame. Then you can see the magnesium strip burning. Now I will write down the steps involved in this activity. The method, you need to get a clean piece of magnesium strip. So, if you have a clean strip is fine, otherwise clean with a sandpaper. So, clean with sandpaper to remove the oxide layer. Then the next step, hold it to the Bunsen flame. Hold it to the Bunsen flame using the pair of tongs. You can see the magnesium strip burn in air. We have already discussed what you should observe. Okay, students. Now we will carry out this activity in the lab. Okay, students. Now we are going to observe one of the properties of magnesium. We'll be using magnesium strips that are available in the laboratory. You can see I have a few pieces of magnesium strip. if you look at this strip, you can see that it has a black color layer over it. It does not look shiny as it is supposed to. So what do? We take a sandpaper and we have to clean it. When you keep on rubbing it like this, it will become clean and shiny. I have already cleaned some pieces of magnesium strip. You can see the shiny nature. So that shows magnesium has the lustrous nature. And also magnesium can be cut into pieces. So using a pair of scissors, I can cut it into pieces. Already I have cut out some pieces. Now we will look at the chemical property, where we burn a strip of magnesium in oxygen using the Bunsen burner. For that, I will be using the goggles because I am going to burn magnesium. And also, I'll be holding the magnesium directly to the flame. Therefore, I will be using a pair of tongs to burn it. And the goggles I am wearing, or the safety glasses, are for the safety of my eyes. Now, I shall hold it directly to the flame. Observe carefully what is happening to the piece of magnesium strip. You can see it's starting to ignite and it is burning with a bright white flame. And once it burns out, you get the resulting white color residue. You can nicely observe the white color residue that has resulted from burning of magnesium. This is magnesium oxide. So from this activity, students, you all saw the observations clearly. What are the observations? Magnesium burnt with a bright white flame and we get a white color residue as the end product. Okay students, now you got a clear observation of the activity of burning a piece of magnesium strip in air. What was the observation? You saw the magnesium strip burn with a bright white flame. So that was your first observation, burns with a bright white flame. And what did you get at the end of the activity? You saw that there was a white color powder or a white color residue, a solid substance which is called a residue or a white color powder. What is that? That is magnesium oxide. That was the second observation. White colored powder remains. So when magnesium burnt in air with a very bright white flame, we get a white color powder as the end product. So from this activity and the observations you got when we did the activity in the lab, we can conclude that magnesium can burn easily in air with a bright white flame and the white powder is magnesium oxide. So that will be the conclusion. Magnesium burns easily in air with a bright white flame and produces a white color powder. So that you know from the reaction is magnesium oxide. So those are the observations and conclusion of the activity to observe the burning of magnesium in air. Now we will do another activity to observe the chemical properties of magnesium. Reaction of magnesium with water. So for that again we will need magnesium metal or the strip of magnesium. Again, as I said, we will need to use a clean magnesium strip. If it is covered with oxide layer, we have to clean it using sandpaper and get the clean magnesium strip that has the lustrous shine. We will need a beaker containing water. So we need water for this activity because we are going to react magnesium with water. But first we will try the reaction with cold water and then we will use water but which is hot. So that is the reason why you are given 2 beakers containing water. We'll do the activities with cold water and hot water. And also we will be using test tubes and boiling tube. So what we can do is we take small strips of magnesium that is clean. Then to a test tube we can take cold water. Put the piece of magnesium strip into it. You can observe that the strip goes down because it's more denser than water. But apart from that, you will not see any change. There will be no change. That means it does not react with cold water. Then what we do is we can either boil water and take the boiled water into a boiling tube or a beaker and put a strip of magnesium and observe the reaction. Or else we can take water into a boiling tube, put a piece of magnesium strip, a clean magnesium strip, and then we can heat it in the Bunsen flame. So either way we will do the reaction of magnesium with hot water. Now we will write down the steps related to this activity. The method, first you have to clean the magnesium strip if needed. So if you already have a clean magnesium strip, you can use it. Otherwise, you have to clean it. This is done using sandpaper. Then the first activity is to react magnesium with cold water. So we can put the magnesium strip into a test tube containing cold water. This is to observe the reaction of magnesium and cold water. Then we can take a boiling tube containing water, put the magnesium strip into it, and we can heat it in the Bunsen flame. Otherwise, we can directly put a piece of magnesium strip into hot water. So, the next step, take a strip of magnesium and put it into a boiling tube. Here we need to use boiling tube because we have to heat the water. Tube containing water, and then we heat the water. Then you can see the change taking place. Okay students, this is a simple activity. So let us try this out in the lab. Okay students, now we'll do the activity to test how magnesium reacts with water. As you know already, magnesium is a reactive metal. It is available as magnesium strips in the laboratory, and the strip is usually oxidized and has a black color layer over it. We can clean it using this sandpaper. If you just place the magnesium on the table and rub it continuously, it will become clean. I have already cleaned a few pieces of magnesium strips, and here you can see the shiny magnesium metal. And also it can be cut easily with a pair of scissors. Already I have cut out a few pieces of magnesium. First, I will do the activity using normal water. Water at room temperature. So, I will need a test tube. To that, I will take a small amount of water, and into that, I will put a piece of clean magnesium strip. You can see because of the higher density, magnesium has gone into water, but you can observe clearly even when I rotate, there is no change taking place. You can nicely observe the surface of the magnesium strip. There is no change taking place. That means magnesium does not react with cool water. So, I will place it in the test tube rack, and now we will see whether magnesium reacts with hot water. As you know students, if we are going to use the burner for heating, we can't use the test tube because that is made up of thin glass. So, I will need to use a boiling tube, and also I will be using goggles or safety glasses for the safety of my eyes. So, I will take a boiling tube. Into that, we take a little amount of water, and to that we can put a piece of magnesium. Also, I will use a test tube holder in order to clamp the test tube and hold it to the flame. And we can heat water. You should take care students, when heating substances inside the boiling tube, we should make sure that we shake the boiling tube very slowly. If you just hold it directly to the flame, there is a possibility that there can be a breakage, cracking of the boiling tube. Although it's a boiling tube, you have to make sure you provide heat evenly. We will have to wait till the water becomes hot. Now you can see there are few gas bubbles being produced around the magnesium strip, and the magnesium strip is also floating because of the water being boiling. You can observe the gas bubbles around magnesium strip. As you know, when magnesium reacts with water, it will evolve hydrogen gas. So that means the gas bubbles around the magnesium strip are hydrogen gas bubbles. So here again you can observe the gas bubbles very clearly. So students, with this activity we can confirm that magnesium does not react with normal water or room temperature water, but it reacts with hot water and evolves hydrogen gas. Okay students, now you observed the activity of reacting magnesium with cold water and hot water. What happened with cold water? Did you see any change? No. So there is no reaction with cold water. So the first observation, no change when magnesium was put into cold water. Then what did we do? We heated the magnesium strip that was present in water in a boiling tube. Then what did you all observe? You saw gas bubbles around the magnesium strip. So there you can see gas bubbles evolved when the water containing magnesium was heated. Okay, so that means magnesium did not react with cold water, but it reacts with hot water and evolves hydrogen gas. We didn't do any activity to confirm that it is hydrogen gas, but from the discussion we know that it is hydrogen gas. So we can conclude saying magnesium doesn't react with cold water, but it reacts with hot water and evolves hydrogen gas. We observed it as gas bubbles. So now we have carried out the activities to see how magnesium burns in air, then how it reacts with water. We will do another activity to observe how magnesium reacts with acids. Activity: reaction of magnesium with dilute acid. So again we will need the magnesium strip. So we need the magnesium strip or the magnesium metal. Then as acid, we will be using hydrochloric acid, HCl. And you know it is dilute hydrochloric acid, because we will be using the dilute form of acid. And to carry out the reaction, we will need test tubes. This is a very simple activity. We need to have clean magnesium strip, and then we take a small amount of the dilute hydrochloric acid into a test tube, and into that we put a clean piece of magnesium strip and observe. A very simple activity. So the method is to use a clean magnesium strip. So take a clean magnesium strip. As you know, if it is not clean, we can clean it using a sandpaper. Then what do? We take a small amount of dilute hydrochloric acid. I will use the formula HCl into a test tube. Then to that put the piece of magnesium into the acid. Then you can see the reaction taking place. So students, it's a very simple activity. You know what we have to do. Now let us carry out this activity in the lab. Okay students, now we will do the activity to observe the reaction of magnesium with acids. For acids, we use dilute hydrochloric acid. So you can see the label. It has been labeled as DIL HCl. That means it's dilute hydrochloric acid. We can do this activity in a test tube. So I will take a small amount of hydrochloric acid into the test tube. And we are going to test the reaction of magnesium with hydrochloric acid. As you already know, magnesium is a metal. It reacts with air and forms the oxide layer. And we can clean it and take the shiny magnesium strip. Also, we can cut it using a pair of scissors because it is a soft metal. So, I have already cut out small pieces of magnesium. I will take one of those strips and put it into the test tube containing hydrochloric acid. You can see immediately it reacts with hydrochloric acid and the gas bubbles are being evolved. Normally, when a metal reacts with an acid, it produces a salt and evolves hydrogen gas. So here the gas bubbles that you are observing is hydrogen gas bubbles, and the reaction is somewhat fast. So students, observe carefully the evolving of gas bubbles, and if you listen, you can also hear the sound of gas bubbles evolving because it is a fast reaction. Okay students, you have observed what happens when magnesium reacts with dilute hydrochloric acid. what did you observe? You saw the gas bubbles evolving around the magnesium strip. And also you saw the magnesium strip dissolve in acid. So those were the observations. So you saw evolving of gas bubbles. Bubbles evolve. And you see the magnesium strip dissolves. So this shows that magnesium reacts fast with dilute hydrochloric acid. And from the knowledge, we already know that the gas bubbles that are evolved are hydrogen gas bubbles. And magnesium reacts with HCl to form magnesium chloride. So the conclusion of this activity is that magnesium reacts rapidly with dilute HCl. Here when I write as DIL, that means it's dilute HCl to form the salt magnesium chloride and evolves hydrogen gas. So that was a very simple activity and you saw the observations clearly. With this, we have clearly discussed and observed the chemical and physical properties of magnesium. Now we will discuss the uses of magnesium. Uses of magnesium. Production of alloys. When we say alloys, this is a combination of two metals. You all know metals as individual metals have certain properties that is useful to us. But when we mix metals together, we get new, better properties which are more useful to us. So therefore, man mixes different types of metals and forms alloys. So one alloy that can be prepared using magnesium is magnesium. Magnesium is an alloy that is made up of magnesium and aluminium. So from the name, magnesium and aluminium, magnesium. That is the example of an alloy that is produced from magnesium. Production of medicines. Magnesium or its compounds can be used to produce medicines. One example is milk of magnesia. Milk of magnesia contains magnesium hydroxide. It is an antacid. When we say antacid, a medicine that is used to control or reduce acidity, gastritis or acidity, which is related to the digestive system. So magnesium can be used to produce milk of magnesia. Magnesia. This contains magnesium hydroxide. Another use of magnesium metal, it is used as a metal that prevents corrosion of iron. So normally iron is a good metal that is highly used in our day-to-day lives, but it can corrode easily. If there is a huge structure that has been made with iron or steel, if it corrodes, then it would become a problem. So to prevent corrosion there, what they do is, in between the structure, for example, a huge bridge made out of steel, in between they insert a strip of magnesium so that magnesium undergoes corrosion but prevents iron from getting corroded. So that is why magnesium metal can be used to prevent corrosion of iron. So students, now we have discussed the properties of magnesium, chemical and physical properties, and the different uses of magnesium. So far we have discussed magnesium and sodium. They are two metals. Now we will look at a different type of elements, the non-metals.